We're going to go through condensers now, chapter 22 in your book. Let me get this pulled up. All right, so evaporators. We're going to go out of order here, but evaporators, condensers, metering devices, and compressors. I know that's not the order that it happens, but that's the way we're going to cover them. So um, the evaporator and the condenser are pretty similar in that they're both usually some sort of coil. They're both going through a latent change. They're both moving heat, either rejecting or condensing, or rejecting or attracting heat. So they're very similar in the way that they operate. They both have latent and sensible things that happen inside of them. So shouldn't be as big of a deal to understand a condenser if you understand your evaporator. It's just kind of opposite. So condenser's job is to reject heat. One thing that we want to deal with and learn is condenser splits, or what sometimes you'll hear me call CTOA, which is condensing temperature over ambient. So that's your outdoor plus whatever. A lot of times outdoor plus 20 is kind of our basic rule of thumb. And then depending on the efficiency of the system, we may run higher or lower than that. Subcooling occurs in the condenser, just like superheat occurs in the evaporator. And that is additional heat that's removed from the refrigerant past the point that it becomes 100% liquid. Sometimes you may have to have low ambient controls, which means if you're going to try to run air conditioning when it's getting cooler outside, in the case that you need to run AC all year round, you would have to have low ambient controls that protect the condenser and protect the compressor, keep everything running right, and maintenance. So just like the evaporator, maintenance is kind of a big deal. Water cooled, cooling towers, things like that we may touch on. So there's three things that happen in a condenser. So in an evaporator, there's only two things. In the evaporator, it is evaporation, which is latent, and superheat, which is sensible. Now, once we superheat refrigerant, we take it into the compressor and we completely, or we compress it, and we don't change its states. We just raise its temperature. We raise its superheat. So the first thing we have to do is remove that additional superheat that occurs in the condenser or in the compressor. So since you can't do a sensible and a latent change at the same time, in order to actually start condensing, I've got to get rid of the superheat first. So the first thing that happens in the condenser is desuperheating. So that is sensible cooling of discharge vapor or hot gas. So you're actually dropping its temp down until it meets its saturation temp. So that's another reason why you don't want any more superheat than you have to have. You don't want to be above what you're shooting for, because you got to get rid of that. And so your compressor, magnifies that, and then your condenser has to deal with it. So if you got higher than normal superheat coming into the compressor, then you're going to have higher than normal discharge superheat, and then you're going to have to get rid of all that through the desuperheating process before you can ever start to condense, which on a high temp day outside, when it's needing all of that anyway, you may struggle because now you got more heat to get rid of than you need. So keeps your efficiency down if you can keep those numbers in check. They're saying first 10 to 15% of the condenser. Yeah, that's probably about right. It's really not something that we're measuring per se, but you could measure it. I mean, you could calculate what it is um, based on, because you can do a discharge if you have the way of a way of measuring discharge pressure, which a lot of times we don't. But if you do, you can measure discharge pressure, or in like commercial units, you can measure discharge a lot. You can measure discharge, and then you can just do superheat of the discharge line, just like you would superheat of the suction line. You would just measure line temp compared to refrigerant temp, and then you can subtract that with its saturation point, which is going to tell you, the discharge or the superheat that you're removing. I know that's confusing, so don't worry about all that. Basically, you're not worrying about it, but you just need to know that it's there. Condensing is the removal of latent heat from the evaporator. So you picked up heat in the evaporator. Now you got to get rid of it in the condenser. Subcooling is cooling it beyond its saturation point. So once it's 100% condensed, just like in the evaporator, you're going to go a little bit farther with it. One of the main reasons for that is to make sure that you're properly feeding your metering device, your TXV. Now, in this picture here, you'll notice that there actually is what we call a liquid receiver. A lot of residential systems aren't going to have this, but some commercial refrigeration setups will, to where it actually has a liquid receiver that will store excess liquid, and then that way the TXV always has a little extra liquid to work with in case it were to not get what it needed. All right, so condenser split. This is the difference between the condensing temp and the air entering the condenser or outside ambient. So this is your outdoor plus 20 that we kind of operate under. This slide's a little old in that it operates under a 30-degree split. So anything that's like low efficiency 22, which would be 10 SEER and below, there are still some of those out there. Don't be surprised if you see a 30 to 35 degree condenser split. So instead of running outdoor plus 20, you may be running outdoor plus 30 to 35, and it'd be running just like it's supposed to. So that's just another efficiency sacrifice. So, whenever those units weren't as efficient, they couldn't reject the heat good enough and well enough. And so you run a higher condenser temp, which means you run higher pressures, which means your compressor has to work harder, and you get rid of less heat in your house. So as they increased efficiency, if you run a 20-degree split, now you can run, you can do the same amount of work or more, and it's running less pressures, which means it's, less amps, takes, a lot less work to do the same job. So now you're running 115 instead of 125, which means you're running 243 psig instead of 278. So that does give you a little bit of an efficiency boost there. And that's one of the things that as systems are getting more efficient, one of the things you'll notice is that the outdoor units are getting huge, because that big coil is allowing you to reject a lot of heat. So it doesn't have to make multiple passes. It can just go through that condenser and get rid of it and do it more efficiently so it can keep its pressure down. Common rules of thumb, like I said, the higher the efficiency, the lower your condenser split. So if you've got a 16 SEER two-stage system or something, you're probably going to run a 15-degree condenser split, CTOA. If you're running a 13, 14 SEER equipment, and I know we haven't talked about SEER a lot, but SEER is just the efficiency rating that they're all kind of rated in. But if you're running a standard efficiency, which now is 14 is minimum, you're going to be running probably a 20-degree split. And then if you're running an older system, you may see that 30-degree split. It's just a different emphasis. At the time, they were just worried about getting cooling. They didn't have the technology. Now it's starting to catch up, and it's getting to the point that, some of this really super high efficiency stuff is running really, really low splits because they can reject all that heat without having to do a lot of work. And that all comes back to savings. Subcooling, hopefully you know how to calculate this. Strap a thermometer to your liquid line and measure your liquid line's saturation temp. Subtract the two. Your line should be colder because it's subcooled, and you're going to usually run about a 10-degree subcooling. It protects your metering device from getting flash gas, getting gas to it. It increases efficiency, increases performance as well. Okay, so for example, this is theoretically, and you got a sight glass on here to see what you're dealing with. Theoretically, if you got 0 degrees subcooling, sight glass is full, but by the time you run it up this line and get it up to the attic, you're going to lose pressure, which means your temperatures are going to change, which means now you're going to flash off some of that refrigerant, and you're going to cause some of that liquid to become vapor. Now that vapor is going to enter into your TXV, and it's going to cause it not to operate properly. So that's why you need a little subcooling. So it's just a long drawn out way of saying you need some subcooling. Low ambient conditions, anything below 60 is considered low ambient on AC. Normally, you're not going to run 60 degrees or below on air conditioning, and if you do, you're probably going to have some low ambient control. That doesn't mean it's always the case. Like you could run, an air conditioner year round, but you're going to have to put some sort of controls on it to make it operate in those conditions. And usually by doing that, without getting too in detail with that, because like coolers, for example, they're running cooling year round. So you've got to have something in place, and there's different ways to do that. One of the common ways to do it, even on an air conditioner, is cycling your fan, your condenser fan. So your outdoor fan motor, you can actually slow it down or cut it on and off to make it maintain head pressure. You have to have a certain amount of head pressure to feed that TXV, or it'll end up starving your system. It won't work right. So you got to have enough pressure to feed that TXV and keep it to working. So killing the fan on low ambient conditions is one way to do that. A lot of manufacturers will recommend that if it's 55 or below, that even when you set charge, even if it's in heating or whatever, that you come back when it gets above 60 or whatever, and you set your charge and make sure everything's right. I'm not getting into this right now. This gets into commercial stuff. Flooded condensers, not getting into that as well. Cleaning your condenser. Good way to clean your condensers. Don't use pressure, a lot of pressure. If you use a pressure washer, you need to really know what you're doing, because I've seen people just completely destroy a coil by sticking a pressure washer to it. Even same way with a water hose. You got to really watch what you're doing. Um, it's better to clean it from the inside out, because air is getting pulled from the outside in. So instead of pushing all that deeper in to the coil, it's better to just try to push it back out. Use some sort of non-acidic coil cleaner that's designed for your type of condenser. So if it's aluminum or if it's not aluminum, that may make a difference. But they make all kinds of cleaners for that. And these are old, but there's still stuff like that and stuff that's better now. Indoor condensers. So if you're working on an ice machine or a cooler or a whatever, you may have condensers inside that need cleaned quite a bit. A lot of those don't even have a filter on them, honestly. Um, Kitchens and stuff, they're really bad about grease getting on there, and then all that dirt gets attached to it. So cleaning those is anytime I'm working on a kitchen area, I'm always checking those condensers. Not going to go into micro channels too much right now. I'm not a huge fan of those myself, and they're kind of not as popular as they used to be. Tube and tube condensers. Um, One way that you can use water instead of air to actually condense. So a lot of coolers, ice machines, freezers, even AC systems, commercial, will use water as a condensing medium instead of using air. So that way you don't have to worry about outdoor air temp. You can run a cooler year round, because it's completely, it's not dependent on outdoor air temp anymore. It's dependent on water. So you use water in, water out, and that water gets transferred. The heat gets transferred from the refrigerant to the colder water, and as a result, the water heats up and then either gets recirculated or gets dumped down the drain. So here's an example of one of those in place on a system. You got refrigerant and water. We're not going to talk a lot about that right now, but we will later. But I do want you to know that that is something that is very prominent, is water-cooled systems. Geothermal's getting into this as well. You know, when you're using geothermal, you're using water. A lot of new school buildings and hospitals are using geothermal loops, so you're going to run into that a lot. It's the same process. Hot goes to cold. You'll use a regulating valve on that. Like I said, I'm not getting into that too deep, but water regulator, actually, as I mentioned in the last lecture with evaporators, your if your water flows too fast or too slow, it'll affect your head pressure. So you can adjust that water flow and kind of make it do what you want it to do, which is pretty cool. And it's just got a spring on it, increase and decrease. We'll get into that a little bit more when we get into commercial setups as well. So I'm kind of going to skim through a lot of this. I think we're about done with that. Remote condensers. This is something that you'll see a lot in commercial setups, to where you don't have a compressor outside. All you have is a remote condenser, which just means they pump the hot gas outside and blow it through a fan coil, blow a fan across it, and then bring the liquid back in, and then everything else is internal. So you'll see that a lot on commercial setups. All right, so that's that. Really not a lot. Once again, I mean, if you know how to measure subcooling, you're in pretty good shape there. Um, Keeping them clean is a big thing. So we'll learn how to properly clean one. And really, honestly, there's not a lot that can go wrong with the condenser other than getting a restriction in it, getting a hole in it. So we'll replace a condenser possibly, pull one, put one back in. It's a pretty big job, so it's not something you just want to do all the time. But it is something you will have to do on occasion, especially under warranty jobs that don't want to replace the whole system. So you'll have to do that. So that should do it for condensers.